Hello, everybody, and welcome to this Open Hexagon Devlog on online leaderboards. I've been working on this feature for quite a long time, and I think it's time for me to share a little bit of my progress and how it works, and some details on the measures I've taken to reduce the possibility of cheating and sending fake scores to the server. So this terminal on the right is going to be our server, which I'm going to start right now. When it starts up, it generates some public and secret keys by using the Sodium library, which is pretty good. And then on the left terminal, I'm going to start the client over here, which is the game itself. Now, when the client connects, when the client starts, it tries to connect to the server with the IP that's in the configuration file. If it does find a server by sending some, handshake packets, the server and the client are going to share public keys. And when their public keys are both, received, they are going to compute some receive and transmit keys from those public keys and their own private keys in order to encrypt packets and make communication a little bit more secure and make it a little bit harder to send fake packets to the server. So once you start a client, it's going to try to connect automatically. When you connect, you are not yet logged in. So you would have to register and log in through the game UI. So I'm just going to delete my account right now to show you the process. And I'm going to register. I'm going to enter a username and a password. And I'm going to get some feedback from the server. As you can see here, what's happening is that, first of all, the client and the server both validate the Steam ID. So I'm using some Steam API that is called encrypted tickets to basically ensure that the current user Steam ID is not spoofed and it's valid, which makes it a little bit harder to spoof your Steam ID. And then this Steam ID is going to be also validated by the server, which is going to store it as the key, the primary key for the user in the database, so that basically we can have a single registration for Steam ID and makes it a little bit harder for people to, spam new accounts and stuff like that. So once you register, you're going to be in the database, which, by the way, is a SQLite tree database. I didn't think about doing anything fancy than that. I think it's going to work fine for this project. Then I can log in for the in-game UI. And when I log in, the server is going to generate a time token. So it's going to generate some random token and a timestamp of the current time on the server. And this token is going to be valid for some amount of time after that's been generated. And now the server expects all the client's packets to contain the token. And the server is going to verify that the token is still valid when the packets are received. Okay, so now let's take a look at the leaderboards. I have some scores here that I was playing around with, but let's change to some different difficulty where this one doesn't have any score. And you can see that you have this real-time display of the leaderboard on the menu screen. The way it works right now is quite naive. There's basically a client-side cache that requests leaderboard scores like every 6 or 5 seconds, and then it displays them. And there's like this kind of like event-based system where the client can spawn events like I've received new scores, and the cache is going to be updated by that. By the way, one other thing I want to mention is that pretty much nothing is multi-threaded here. It's all running on the same single thread, and that's a deliberate decision. I didn't want to deal with multi-threading at all. I think I wanted to have a very simple and easy to reason about model for the server and the client. So every frame, basically the client is updated, checks if it needs to send something to the server, checks if it has received something from the server. If it has received something from the server, there is a list of events, which is basically a set variant. So it's a sum type, and it adds stuff to this list. And then the components that are listening to the client, like the menu, the game menu, or the game itself, can pull this list of events to figure out what the server replied or what happened. Same thing with the server. The server has like a list of connected clients. Each connected client has its own socket, and then I'm using SFML's socket selector API to pick any socket that has data basically in a loop. And again, there's no multi-threading here, so it's going to use internally. It's going to use some sort of like OS API like select or epoll to pull the sockets efficiently, and it seems to work quite well. Okay, so let's try to set up a score for this particular level. Yeah, it didn't go really well. Let's make something a little bit better. So we got a score of 9.6 seconds over here. If I go back, I will see it in the online leaderboard. So what happened? If we look at the server logs, we're going to see a few interesting things. So first of all, whenever a client starts a game, so whenever a client tries to start, a new record, it sends a packet to the server. And the server receives this packet here, and it says client start a game for some level with some level ID. And now the server is going to generate a timestamp for that client that remembers what was the last time the client started a game. Then, when the client is done with their playthrough, they will send a replay file which contains all the inputs per frame to the server. The server will then replay that file internally, and it will, figure out if the replay is valid or not. It will figure out the final score by replaying the same inputs that the client produced. And this is what you see over here. It says replay processed, final time 9.6 something. And now the server is going to be a little bit clever, and it's going to check, okay, I got my replay and I got the replay at some other timestamp. So what's the difference in time between when I received the packet that said that the client was starting the game and the packet with the replay data? In this case, it's going to be quite similar to the final time. So right now there is like a very stupid threshold, like 3.5 seconds or 4 seconds, something like that. And if the outcome of the replay, which is 9.6 seconds, is not too different from the difference between the initial game start request and the final replay sent by the client, then the replay is going to be validated and is going to be added to the database. And this is like a security measure in place to prevent cheating with something like Cheat Engine. You could use Cheat Engine and slow down your game. Actually, I'm going to do right now. Let's see if I can make that work. So if I can use Cheat Engine, I can open up my process over here. Let's see which one is the right one. The one using more memory is going to be the one that's the client. So 24324, which of course is going to be this one. Okay, so I can enable speed DAC, maybe make it a bit slower. Let's say half as fast, 0.5. As you can see now, the simulation is way slower. Okay, so that should be enough. As I got this replay, the final time was 6.3, which is what you see in game, but the difference between the first initial request where the client started a game and when I received the replay is about around 12 seconds, which explains the 0.5 speed modifier over here. The difference is too much, so it's going to discard this replay because it's likely to be cheated, or there was some slowdown issues or stuff like that, so it's going to be discarded by the server. And you can get around this if you're clever. You can intercept the first packet and then send it later to make it work, but it's a pain, right? And it's never going to be 100% foolproof, but at least it's going to stop most people that want to cheat by using something like a speed DAC or something like that. It's going to make it a little bit harder, and I think it's a quite easy security measure to implement in this case. In terms of implementation, this is all C++, modern C++. If you look at the way it works, basically I have these packet types over here, which are basically just simple structs. And then I'm using some macro and metaprogramming magic to basically automatically generate serialization, deserialization code for the structs, using some basic reflection, using some library called Boost PFR, which is quite nice, and some handwritten stuff to basically recurse over the packets and encrypt them and decrypt them and stuff like that. So it's really easy to add a new packet type and remove packet types. You just add a new struct, add it to the list, and if the fields are serializable, that's all you have to do. And then in the client and server, I have this big match statement, which is basically my own version of pattern matching. Let's see if I can find it here. And basically, whenever the client, for example, receives data from server, which is going to be an SFML packet, then it's going to do this match. and I have a lambda expression, so an anonymous function for each packet type, and these are all going to be overloaded for me, and this is every handler for every single packet type, and that's pretty much it. So very easy to add new packet types to experiment around, and I enjoy this kind of like meta programming to make my life easier. So this is, in a decent state. There's a bunch of stuff that I need to do before release. Of course, one of the things I have to do is fix a long-standing bug we replace. Sometimes, like 1,000 times, the replay is corrupted, is invalid, and I have no idea what's causing it. I have like an automated test set up that plays the game constantly and tries to find a mismatch in replay. Doesn't find anything. Um, I've checked the code multiple times, tried to find undefined behavior or memory corruption errors with sanitizers and stuff like that. Nothing came up. So there is this weird bug that sometimes when you're doing your playthrough and you finish and then you replay your playthrough, then it's going to be out of sync for some reason, which doesn't really make any sense to me because first of all, the game logic is fully deterministic. The random seed is stored. The update loop is again deterministic. It's using a time slice based update method. Is not dependent on FPS, and most of the times it works. So it's just like 1 in a million times it just gets screwed up, and I don't know why. And the automated test cannot find that. So it's going to be a bit painful. It's probably going to cause some replays to be rejected when the leaderboards are uploaded to the Steam version of the game. But that's what we have so far. And apart from that, I also need to set up some sort of like backup system for the database, some sort of way to recover your password if you screw up and register, make a typo, and then you can't log in anymore, but you cannot delete your account because you don't have your password. So a bunch of stuff like that. And apart from it, I think it's almost ready. So just some polishing, some bug fixing, backup system, password recovery, should be ready for a more public beta on Steam. I'm gonna stress test it a bit, and then it's probably gonna hit mainstream, I guess, in a week or two. So yeah, I hope you enjoyed this devlog. It's something that I haven't done before. Let me know if you wanna hear more, you wanna see and hear more about the development process of Open Hexagon. These videos are quite, easy to make. I just talking about what I've done in the past few days or weeks. And yeah, stay tuned for the leaderboard system and enjoy Open Hexagon. Cheers.